Welcome to The Explainer. Today, we are diving into something genuinely historic. Look, if you've ever taken a computer science class, or honestly, even if you've just used a GPS app to find the fastest route to a coffee shop, you've interacted with the foundational math we're talking about today. We're unpacking a massive July 2025 paper that completely shatters a fundamental barrier in algorithmic design. And I mean a barrier that has stood essentially untouched for over 6 decades. For generations, computer science students have been taught that when you need to find the shortest path in a network, Dijkstra's algorithm is it. It's the gold standard, the textbook champion. But this new 2025 paper poses a highly provocative question, one that has stumped experts for literally decades. Is Dijkstra's famous algorithm actually optimal, or have we just been stuck at a mathematical roadblock all this time?
Right off the bat, let's look at this absolute mic drop of a quote from the 2025 paper by Duan, Mao, Xu, and Yin. They explicitly state their research is, quote, showing that Dijkstra's algorithm is not optimal for SSSP. Honestly, that single sentence fundamentally rewrites graph theory as we know it. But to really grasp how monumental this is and how they actually managed to prove it, we need to set the board and look at the exact problem they're solving.
Section 1. The shortest path problem.
Before we can break the algorithm, we gotta understand the SSSP, or the single source shortest path problem. Imagine a map of a city with one-way streets. In graph theory, we call that a directed graph. Now, those streets have varying lengths or traffic times, which we call non-negative real edge weights. Your goal? Find the absolute shortest travel time from your starting point, the single source, to every single other intersection or vertex in that city. By defining SSSP clearly, we can see exactly what these researchers were trying to optimize and why it is just so incredibly difficult to do it fast on massive networks.
That brings us to Section 2, Dijkstra's reign and flaw.
Picture this. The year is 1959. That is when Edgar W. Dijkstra published his legendary algorithm. Think about that for a second. We're talking about an era when computers literally took up entire rooms. For 65 years, this algorithm stood basically unchallenged as the best way to solve the SSSP problem. I mean, that is a staggering reign for any concept in modern computer science.
Now, here's the classic speed limit we've all memorized. O of m plus n log n. This formula represents the algorithm's time complexity when it's supercharged with advanced data structures like Fibonacci heaps. In this formula, m is the number of edges, think roads, and n is the number of vertices, or intersections. And this whole thing runs in the standard comparison addition model. That just means the computer is only allowed to add weights together or compare which one is bigger. Now, for really dense networks with a ton of connections, this speed is actually great, but on sparse graphs, networks with way fewer connections, that n log n part at the end becomes a really heavy dragging anchor.
Which leads us perfectly into Section 3, the sorting barrier.
So, why the huge bottleneck? Well, think of the algorithm's frontier as a massive lineup of people waiting to get into an exclusive club. Dijkstra's algorithm works by keeping a priority queue of all the vertices it hasn't fully explored yet. The bouncer at this club must constantly scan the entire line and pick the absolute closest or cheapest vertex to the source to let in next. But to always know who is closest, the algorithm essentially has to maintain a strictly sorted list at all times. If your frontier grows to contain a huge chunk of the graph's vertices, sorting that massive lineup over and over and over again, that causes a notorious delay.
Because of this constant need to sort, the computing community accepted a mathematical lower bound, an unbreakable wall of omega n log n for sorting algorithms. For decades, experts just believed that for directed graphs with real number weights, breaking past this sorting barrier was straight up impossible. It was treated like a law of nature. You had to sort the frontier, and sorting simply took that much time. Period. Section 4. Merging two classic methods.
The 2025 researchers completely refused to accept that law. To bypass the sorting barrier, they looked at Dijkstra's old rival, the Bellman-Ford algorithm. It's a real clash of titans. Dijkstra uses that priority queue, right? Super fast at finding the minimum distance, but heavily bogged down by sorting. Bellman-Ford, on the other hand, relies on dynamic programming and requires zero sorting, but it's wildly inefficient because it just redundantly relaxes all the edges across the entire graph over and over. The brilliant insight here was realizing they could synthesize the best traits of both. They designed a recursive partitioning technique to merge them together.
Section 5. The power of pivots.
Now, we're not going to get bogged down in the dense mathematical proofs today, but conceptually,
Their divide-and-conquer mechanism is so elegant. Instead of putting everyone in a giant, dynamic line like Dijkstra does, they first limit the massive frontier by setting an upper distance bound. Then, taking a page right out of Bellman-Ford, they just run a few unsorted relaxation steps, specifically k-times, from that frontier. By doing this, they effectively solve the easy short paths instantly, with zero sorting required. Whatever is left over allows them to shrink that massive frontier down into a tiny, highly exclusive VIP list.
They call the vertices on this VIP list pivots. By identifying these pivots, they slash the workload down to a fraction of the original size. The algorithm now only needs to focus on the roots of these large shortest path trees. So instead of sorting the entire massive frontier of the whole graph, they're only ever organizing a drastically reduced set of these crucial pivot points.
Under the hood, how does it actually run? It recursively computes what they call bounded multi-source shortest paths, or BMSSP. To handle all this data, it uses a block-based linked list that only requires partial sorting, and it merges new data super efficiently through batch prepend operations. But listen, the absolute most important feature here? It is completely deterministic. In the past, attempts to speed things up relied on randomized algorithms, which is essentially making really educated guesses. Not this one. The 2025 algorithm uses zero random guessing. It mathematically guarantees the speedup every single time you run it.
And boom, here is the ultimate result. The new speed limit, O of m, log to the 2/3, n. Because they successfully bypassed the need to maintain a fully sorted priority queue at all times, that old n log n barrier is just gone. This new time complexity officially shatters the 65-year-old bottleneck, running significantly faster on sparse graphs than Dijkstra's algorithm ever could.
Finally, Section 6. A new era for graphs.
You really cannot overstate the impact of this 2025 breakthrough. It's basically the holy grail in algorithmic design because it checks all the absolute hardest boxes at once. It's the very first deterministic algorithm to break the bound on sparse graphs. It works perfectly on directed graphs. It allows for real, non-negative weights. It operates entirely within the strict boundaries of the standard comparison addition model. And, most historically, it conclusively proves that the algorithm taught in literally every computer science classroom around the world for the last half-century is mathematically not optimal.
It completely reminds us that in the world of computer science, even the most established, rock-solid laws can be rewritten if you just look at the problem from a fresh angle. Which leaves us with a pretty fascinating question to ponder today. With this supposedly impassable sorting barrier finally broken, what other deeply entrenched, quote-unquote optimal algorithms sitting in our textbooks are just waiting to be dethroned? Thanks for hanging out for this explainer. Keep asking the big questions, and we'll catch you next time.